Okay, now we're going to move on to one of the most valuable tools that Python provides, at least within a biomedical informatics context, and that is regular expressions. So regular expressions are an integral part of many research projects. Essentially, regular expressions are compact pieces of code that allow you to match, extract, or substitute complex textual patterns. Some applications include decision support, where you might be extracting the pertinent medical information from a text archive, public health, where you're extracting names, locations, and dates of deaths from obituaries, or kind of general natural language processing, where you're, for example, finding negation phrases in a report to see if a finding is actually present in a report. So, are regular expressions fun? Maybe, but here's a quote from a previous textbook that I've used. If you've heard about regular expressions before, you probably know how powerful they are. If you haven't, prepare to be amazed. You should note, however, that mastering regular expressions may be a bit tricky at first. Okay, very tricky actually. I think that of all the topics that we're going to cover, regular expressions are the most confusing and complicated in terms of just how often I find myself banging my head on my desk, looking at a regular expression, and not being able to understand why it's not doing what I expect it to be doing. In fact, when I was preparing the notebook for this presentation, I just had many of these occasions where, what? Why isn't that working? So that's going to be something that you're going to have to kind of deal with, but just kind of go at it with eyes wide open and tackle it with courage. So just kind of a historical note, in very old versions of Python, regular expressions were different. They were based on Emacs, and at version greater than 1.5, they switched to a Perl style regular expression, and that's what we're going to be working with in the class. So a note about building regular expressions. You always want to build regular expressions with raw strings. And we haven't talked about this, but just like there's Unicode strings, there's raw strings. And you create raw strings by preceding the string definition with an R. See, I'm missing my little quote symbol right there. Sorry about that. So this is a raw string, and the important thing about raw strings is they don't evaluate special characters in the string. And this will become important because regular expressions will be built using many special characters. Okay, so let's get into this real slowly. And so I'm going to import the regular expression module, which is RE. That's the version we're going to use. And I'm going to create a string that just has some names in it, where sometimes I've capitalized them, sometimes I haven't. And I'm going to create a regular expression. And the way I do that is with the compile function in the regular expression module. And it takes as an argument a string, which is defining the regular expression, and then there's some optional compile arguments that will illustrate at least one of them later. So one of the there's multiple methods that the regular expression object that we've created has, but for now we're just going to use the find all. So find all takes a string and finds all occurrences of matches of that regular expression. So let's evaluate this, and you can see that in this case it found the one instance Brian. It didn't find this because it's case sensitive. Okay, so I can make the regular expression case insensitive with a compilation flag, and that can be done either there's re.ignore case or re.I as an abbreviation for the ignore case. And if I create my regular expression with the compile function with these flags present, the regular expression will be case insensitive. So let's demonstrate that here. So in the first case, the original regular expression, I just catch Brian, and with the other two, I get either Brian with an uppercase or Brian with all lowercase. Okay, the real power of regular expression comes from meta characters. And the meta characters that are used in Python are listed right here, and we will go over some but not all of these in today's exploration. So the first meta characters to look at are the square brackets. So square brackets are used to specify a character class, which is a set of characters that you wish to match. So I could do ABC, which I could alternatively specify as A through C, so those are equivalent. A through Z is all lowercase letters. A through Z and A, capital A, okay, that's another typo. That should be like that to match all alphabetical characters. And A to Z, another typo, A to Z, and 0 to 9, this would match all lowercase characters, all uppercase characters, all digits. Okay, so let's just create a test string that's our alphanumeric characters and look at a couple of different regular expressions that we can create. So in this case, I'm using a character class where I'm going to match A, B, or C. And then I'm going to find all the ones that I match, all the ones that match and print it, and then I'm going to repeat that just using the different syntax of A through C. And you can see in this case, we get the characters A matched, the character B matched, and the character C matched for both regular expressions. Okay, so now if we want to match any lowercase letter, we can specify that through this A through Z. And when we do this, we're going to get you can see here we've matched all the lowercase letters. And it's each character is a match individually. And here we will just match all lowercase, uppercase, and digits, which is basically our whole string. Okay, so you see that here we specified a character class, and what we matched were single characters were considered a match. So we can specify the class size of how many characters go together. And this is specified by various meta characters. So the asterisk matches 0 or more characters. So 0 through 9 matches 0 or more digits. The plus matches 1 or more characters in the character class. The question mark matches exactly 1 character. And the curly bracket with an integer, comma, integer matches at least m characters and at most n characters. So question is, how could you express the asterisk, plus, or the question mark with m by n syntax? Well, that's a good question. So for the asterisk, 0 or more, m would be 0, and I'm not exactly sure what n would be. The plus would be, m would be 1, and again, not quite sure what n would be. We'll have to explore that. And a question mark, exactly 1 character, m would be 1, and n would be 1. Okay, so then let's just look at some examples here. I'm not exactly sure what I'm doing here with this R9 from these previous notes, but here I'm matching an A followed by a B, C, or D, any number of those, so I could have 0 or more matches of that followed by a B. So if we think about what should we expect to match, so if in our test string we just have A, B, C, D, that an A, I don't have anywhere where I have an A, B, B, or an A, C, B, or an A, D, B. So my only match here would be an A, 0 matches for this character, and B. And what I see that I match is 1 instance of AB. Okay. Let's just take a second and explore the question of the asterisk. Well, we're going to leave that to class. In class, I'll have a little presentation about the details of the asterisk and MN syntax. Okay. What if we want to match something that's one of our meta characters in a character class? So within character classes, meta characters do not have special meaning. So remember, our meta characters, if we scroll back up here, are the caret, dot, period, asterisk, plus, etc. If I put those in a, I'll scroll down here, in a character class, they're just normal characters. And the one exception for that is the asterisk as the first character in the class. This denotes the complement of the class. So that is, if I put the caret at the beginning of something, it means match all characters except those denoted in the class. So here, if we compile here, caret A to Z, this will match any character that is not an uppercase letter. So let's test that right here. And we get our lowercase letters and our digits. Okay. Now let's look at the next meta character. That's the backslash. So the backslash character is used to escape all the meta characters. So to search for a square bracket, you would need to type backslash square bracket. And here's a test example. So I have a test sentence, just kind of meaningless. The range of the function f1 is 0 to 12 inclusive, and the domain is 0 to 144 inclusive. So we might think that might conclude that f1 is a square. So let's run this, and you see that we did in fact match the two right brackets that are present in the sentence. Okay, we can use the backslash to specify special classes of characters similar to the square bracket notation. So slash lowercase d matches any decimal digit, meaning this is equivalent to the class square bracket 0 to 9. So here, another test sentence where I've created a regular expression object compiled with just looking for any decimal digit. Let's evaluate this. And there we go. We got the 7, the 2, the 9, the 8, 4, 1, 0, 8. Okay, so slash capital D matches any non-digit character. This is equivalent to the class square bracket caret 0 to 9. So remember, that's the complement. So anything that's not a 0 to 9. So let's run this cell. And we got all the words minus, and the spaces minus the digits. Okay, slash S matches any white space character. So this is equivalent to, you can't tell it here, but there's a space there, a slash T for a tab, a slash N for a new line, a slash R for, that must be some sort of return, a feed, V, a vertical feed. And so here I started playing with that same sentence, but showing, building the regular expression with either the slash S or the equivalent character class. And just we'll print them out and verify that they are grabbing equivalent features from the sentence. So here's all our white spaces that were grabbed in the sentence. Okay, slash capital S matches any non-white space character. So again, this is equivalent to the class caret for the complement of the space slash T slash N, etc. And so let's run this, and we should be catching each individual character minus the spaces. So see, no spaces. We got a comma and all the words. Okay, a slash lowercase w matches any alphanumeric character. This is equivalent to A to Z, 0 to 9, and it's like an underscore. I don't know why I got an underscore in there, but maybe that's true. Okay, so we compile this again and just using the slash W versus that, and we are getting the same features extracted. So any alphanumeric character has been matched. Okay, as you can see the pattern now, slash capital W matches any non-alphanumeric character with its equivalent character class here. So let's evaluate that one. And well, once you know, I forgot to change my definition here and the regular expressions when I copied it over. So let's change that to a capital W, put the complement in here, and rerun it, and we're back to getting the white spaces, and we did get a comma in there. This that comma is kind of hiding, so we can print in result 18. So a comma is one of the things that we found. Okay, so let's put these things together to be a little more useful instead of just matching single characters. We showed you how to use the size of the character class. So here we have sentence, my work address is 729 Airpine Drive, Salt Lake City, Utah 84108. And so let's look at how we can find the zip code. So zip codes, ignoring the kind of the optional dash and then the 4-digit code, is a 5-digit integer. So we can do it one of two ways. We can use the /d and then specifying that we want at least 5 and at most 5 numbers to match. Or we can do a 0 to 9 and match at least 5 and no more than 5 numbers. And so let's run that. And we got the 84108. Okay, what's something else we might want to match? Well, we might want to match telephone numbers. And so I took from the University of Utah web directory, just searching for Chapman's. I've saved that as a text file here that I will upload onto the website. But it's a big, nasty HTML file. There's a lot better ways of identifying things in HTML, which we'll go over later, than just building your own regular expressions. But here I've created a regular expression where I'm looking for the 3-digit area code. So 0 to 9 matching at least 3, at most 3, then a dash, and then 0 to 9, at least 3, at most 3, dash, and now just to kind of illustrate the equivalence of the /d, at least 4 digits and at most 4 digits. And we can print all the names, so all the phone numbers. So let's look at that. So here are phone numbers. And you'll note that this kind of requires that we know the format of the numbers. And next, we'll pick up on this in a later class when we talk about groups and optional things. We may want to look at where there's optionally parentheses around the area code, or no area code is provided at all. And those are all things that we can easily do with regular expressions. Okay, so that was phone numbers. How about finding names? So let's think about two formats. So I might have a name specified as like Brian Chapman, but also in other contexts it might be last name first, first name last, separated by a comma. So let's make regular expressions to look for words that match in this pattern. So in general, I think this would be very hard to match because it's just 2 words, but we do have the information kind of to help us that in this case of a proper name, the first letter is going to be capitalized of the first name and the last name. Certain Dutch names as exceptions that would have to be dealt with in a more complex regular expression. So let's try that first. So what I want to look for is any capital letter, a single character, matched by 0 or more lowercase letters. Now, maybe what would make the most sense here would be at least 1 character instead of 2, but let's leave that as it is for now. And then at least 1 white space of any form. It could be a line break, it could be a space, it could be a tab, followed by another word that starts with an uppercase letter and has 0 or more lowercase letters. So if I apply this with a text string here, We'll see if we're able to find these names. That's just a test that I ran. Text is what I read my contact phone information into, and so we'll try the same thing against it. And I'm just going to print out the first 20 names. I've also created another regular expression. Well, let's just do that. Let's just split the cell here, and let's evaluate this cell. So we got Brian Chapman, Wendy Chapman, Jeremiah Chapman, so that string all worked fine. Here on our web page, we have certain things that certainly don't look like names, like DX, basic search, campus directory. So these are like headings in the text where they're using the same capitalization rules we use for proper names. But let's see if we print a few more characters out. Let's see. We do get down here and you see that we are getting names. So we're getting Brian E., which we haven't accounted for optional middle names or middle initials. We're getting titles, associate professor, departments, translational sciences, but we are getting names here. Julie Armstrong, Wendy W., biomedical informatics. And that there's more. I think if we kind of just expanded this, we're going to see more and more names on here. Joshua Truman, Catherine Lewis. Okay. Well, let's look at the second format, and that's where we're saying last name, comma, first name. So this is going to be a more specific style of specifying a name than our previous example. So here we have the same capital letter followed by lowercase letters, a comma, and then spaces, at least one or more white space, and then the uppercase, then lowercase letters. So let's look at what we find here. Okay, we found colleges, comma, departments. Okay, not a name, but we got Chapman, comma, Brian, professor, comma, research. So we're still not just getting names, but it seems like we're a little higher density here. So we got a David Chapman, Julie Chapman, Polly Chapman, Margaret Chapman. I have to learn who all these Chapmans are. All right, so that's a simple name finder. A regular expression that obviously needs to be improved, and that will be improved using tools that we'll explore later. So here's just a test string with a bunch of words thrown in it and just some different questions. So find all strings that end in Ithon. Find all instances of Brian. Find all Jython or Python instances. Find all Python or Perl instances, and find all names that start with B. So we'll just go through these one at a time. So regular expression 1, find all strings that end in Ithon. So that would be any A to Z of 0 or more characters followed by Ithon. And we get Python, 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 Jython, Zython, CPython, Python. Okay, now find all instances of Brian, which I'm going to assume includes lowercase letters. Then I can just compile Brian with the ignore case. And let's run this. And I got Brian, and lowercase Brian. Okay, this is illustrating the OR, which is the vertical pipe meta character. This says match Jython or Python. And again, we're going to ignore case. So you see we got all the Pythons and we got a Jython. Okay, similar thing with a Python or Perl, and Python or Perl ignoring the case. And here we got the Perls, and the Pythons thrown in. And kind of last thing, match all names that start with B. So that would be a capital B followed by 0 or more A to Z characters. And let's just run that. And we get Burr, Brian, Brad, and Bob. And if we come up here, we can see that's for B.R. Chapman died. Okay. All right, so that's our first run at regular expressions. I might make another recording before tomorrow but be prepared to play around with regular expressions in a variety of data types.